Next up, we have Kevin Riegel from Akamai, who is going to be talking about how they provide safety at scale. Kevin?
Hi, folks. As he said, my name is Kevin Riegel. I'm a senior security researcher at Akamai Technologies, just up the street. And I'd like to talk with you about safety at scale. So I assume many of you know who we are. For those of you who are new to us, Akamai are the world's largest content distribution network. We assert that we deliver about a quarter of the traffic on the web. And so these numbers have changed since I put them in my slide. We now have 200,000 servers in 110 countries worldwide. So when we talk about having problems at scale, Akamai has problems at scale. A little bit about me. So I joined the information security department, led by Andy Ellis, who some of you know, about 3 years ago. In fact, I think I'm coming up in about a week on my 3rd-year anniversary. I was in software engineering before joining the security team. I joined the safety team, who are responsible for Akamai's incident management process. And in September, I transitioned within InfoSec to head the security architect studio in the arm of the InfoSec organization responsible for design reviews. So my peers are security architects whose job is to work with our engineering business units to help us build and operate safe software. And the folks who report to me, some of whom are in the audience, are young security researchers or folks who are new to the field or just out of college, and we're trying to turn them into security architects. So that's been a lot of fun. If you want to hear me bounce about it, come find me after. The person who I really want to introduce you to is my former boss on the safety team, Michael Stone. So Michael's a great friend. Worked together for a long time, and I learned a lot from him. So he's a mathematician by training, and a theoretician and a scientist by inclination. And so the story starts a little bit before I joined Akamai. He was involved with incident management even then. And the thing you need to know about incident management at Akamai is we use our incident management process for everything. So even if you're working coming out of security, you're not just dealing with DDoSes and people trying to hack us, but you're dealing with every time a piece of code sneezes on the network or some customer typos their config, sorry folks, we call an incident for it and we get folks involved. And so he was seeing a lot of the problems at Akamai, which weren't necessarily related to security things. And there was a period, we had a spate of really bad incidents, which were just like these nasty messes. There were maybe multiple systems talking with each other in ways that the designers hadn't anticipated that was causing problems. It was really hard to separate the pieces of the problem out. It was this kind of nasty Gordian knot. And maybe there were political divisions within the company that were making it hard to solve the problem, or other kinds of issues there. And so Michael had what I'm going to characterize as a crisis of faith. He found himself wondering, how would we know if it were possible to build safe systems at the level of complexity we're working at? And he went, because of his research inclination, he went and did a literature search on this. And what he found was that there is a vast body of literature which claims that what we're trying to do is impossible. There are authors, and I won't name names, who assert that modern systems are simply too complex. They have too many interactions that there's no way that humans, designers, can possibly anticipate all of these interactions. And so really, we're just screwed. We should turn off the nuclear reactors, shut off the internet, and go back to living, if we're lucky, we'll live in some kind of farming paradise like the Shire, but if we're not lucky, we'll be like back in caves banging rocks together. And Michael was really disheartened by this, and spent a while thinking about it. But he, believes fairly uncynically in the power of science and technology to make people's lives better and to make the world better. And so eventually he came to the conclusion that this couldn't possibly be the whole story. There had to be, something that these authors were missing. And partly it was just a practical thing, because convincing people to stop building these complex systems is hard, even if Michael himself could be convinced to cut the Gordian knot by quitting Akamai and going to farm potatoes. There was just no way that other people could be convinced to stop doing this, we've gotten so attached to things like clean water and cheap electricity and cat videos, and that we don't want to give those things up. And moreover, why should we, right? There has to be some way for us to have these things safely. And so Michael did more reading, and he reframed the question a little bit. He scoped it down a little bit. He said, so I got this complex system in front of me, which I want to operate safely. How would I convince myself that I had built it in such a way that I could do so? And well, so those authors thought that that was impossible, but maybe if I add some error bars, because there are only ever going to be 24 hours in a day, and budget is finite, and steel is only ever going to be so strong. So given this complex system, how could I convince myself that I had built and could operate it as safely as possible within the constraints that I'm working under? And then he was going to need a teachable and reproducible method of this, because Akamai had been doing incident management kind of as an art. Like, you went and apprenticed with someone for 5 or 10 years before you got to actually deal with these problems. And Michael wanted to do this at the scale that he was trying. He was going to need he was going to need to be able to teach this to people, and they were going to need to be able to get relatively similar results to each other. In other words, to simplify Michael's question, he was asking, how can we engineer complex systems for safety? And so it was at about this time that, following a chain of references in the books that he was reading, Michael came across a book which was just then in the process of being published, with the promising title of Engineering a Safer World by Nancy Leveson. So Nancy, it turns out, has a computer science background, and she got involved about 30 years ago in the then nascent field of software safety when she got called by some folks who were working on ballistic missiles and who were concerned that their code had bugs, as well they should be. So over the last 30 years, she's worked a lot with the military and with Boeing and with other aerospace sorts of folks. She wrote the Therac 25 paper, which is about a particularly nasty set of failures in a medical radiation device, which killed a few people. Was involved in the Columbia accident investigation, and is these days a professor of aeronautics and astronautics over at MIT. So she's been working on this problem for a long time and has some thoughts about it. So the field that she is now one of the founders of is called system safety. And the safety part is mostly self-explanatory. We talk about safety rather than about security because safety is a broader problem. It's not just freedom from loss of authentication, loss of availability, but freedom from a much larger set of unacceptable losses. And the system part is system as in system theory, or as in the study of control systems. And a control system is really just a feedback loop. And modern software, it turns out, is riddled with these things. So this is the part where I took all the math out. I'm sorry, come up and find me afterwards. 20 minutes was not enough for a brief primer on control systems. So the key insight of system safety is that safety is an emergent property of systems. And so we talk about emergence sort of in a casual sense, but it's got a more formal definition. And there are two pieces of it. The first piece is that a system which exhibits emergent behavior has events in it which are not independent. So my website is not very highly trafficked. I basically just get the spam bots and the search engine crawlers, the background radiation of the internet. And so it's pretty easy to model the visitors to my website as like a Poisson arrival process who have normally distributed inter-arrival times or whatever. And as long as I don't do something silly like present at a conference, it's a really good model of the visitors to my website. And I might not know at any given time whether someone is going to show up, but I can make good guesses about how much time it will be before someone shows up. Now, the NFL's website can also be sometimes modeled using Poisson inter-arrival process, but then there are days like the Super Bowl. And within the context of the Poisson arrival process, I can't talk about something like the Super Bowl because it involves a bunch of people simultaneously deciding to go do something that they wouldn't otherwise have. Their decision to go visit the site their decisions aren't uncorrelated. So the other property of systems which exhibit emergent behavior is that you can't take them apart and understand the pieces in isolation. And the key takeaway from that in a safety context is that a system which exhibits emergent behavior, like the systems we're dealing with, isn't safe just because all of its components are safe. I know we've all had the, like, oh God, why moment when we see people who are buying like a secure router and secure links and secure servers and expecting that that will, a secure firewall, expecting that that will make their company safe. You can't buy all safe components and have a safe system. And in fact, you can have a safe system without safe components. We look at something like Netflix's Chaos Monkey, and not only do they have the problem that EC2 regions go down periodically, but they're intentionally inducing failures in their EC2 servers and in their availability zones in order to build a safe system on top of that. So the key, we call this feature of systems which exhibit emergent behavior irreducible complexity. And really what it means is that emergent behavior does not exist at lower levels of abstraction. You can't talk about an ant hive from the perspective of an ant. You can't talk about a safe system from the perspective of a component. And so what this means is that when we're trying to design systems, we can't constrain their behavior from the bottom up, that's buying all safe components. We have to constrain emergent behavior from the top down. So we need to ask ourselves when we're designing systems, looking at the system at the highest level, what constraints must be true about this system in order for it to be safe? And that turns out to be a really powerful question. And the implications of that, Nancy lays out in the book in 500 pages of detail. There are two methods which she details: the system theoretic process analysis, which is a system for design analysis, and the causal analysis using system theory, which is a accident investigation methodology. Basically, the accident investigation or incident investigation methodology turns it on its head and says, OK, so something went wrong here. What constraints about this system needed to be true in order for it to be safe and weren't? So these have been used successfully in aerospace, in the military, in transportation. About every 6 months, she gets folks together over at MIT for a little mini conference on this. And she has folks come in from all over the place. And it's really interesting to see the places where we're solving the same problem, even though, if you'd asked me when I joined Akamai what effect, transportation, what transportation could teach me about computer security, I would have looked at you like you'd grown two heads. So this is the part of the talk where I wish that I could tell you that we have brought these methods and these philosophies to Akamai, and everyone understood them immediately. Developer productivity is through the roof. We pick them up, and everything's great. The truth of the matter is that it's been really hard. And I would say that we're still digesting these ideas and trying to turn them into things that we can use in Airfield. At one of these conferences, we got to talk with the folks, with a couple of Michael's friends from the Dutch Accident Investigation Board. And they mostly do transportation accidents, train accidents, although their remit is broader, and so they've been involved in some computer security stuff. But we asked them, so how many incidents did they review a year? And they said that, well, they work in teams of about 6. They have about 5 teams of 6, so 30 people, and they review 1 to 2 accidents a year. And I thought, wow, that would be amazing. I don't know about you folks, but Akamai's incident review process handles about 50 incidents a year. And our design review process also does about 50 design reviews a year. We review 50 products a year. So also software moves faster. The Dreamliner spent a decade in development, the new Boeing 787, and an airliner has an expected operational lifetime of 40 to 60 years. I don't know about you, but if the products that I'm reviewing today are still being sold 2 years from now, that'll be awesome. We'll have built something with real longevity. Akamai as a company is one of the old guard, one of the Web 1.0 companies, and we've only been around 15 years. And yet we're building things which are at the same kind of scale as these airliners with the same level of interaction. And that perversely means that we need these tools and techniques much more. In a physical system, right, there are only a limited number of ways that components can interact. You've only got 3 dimensions, and so that constrains the problem somewhat. Whereas in a software system where everything's data, I can have 50 heterogeneous components that I don't control any of talking to a single point. That's Tuesday. That's any that's any website. So really, in order to constrain the complexity that we're working with, we need tools like this, and we need to figure out how to apply them. So I think we're missing critical software tooling. I've been hearing people talk about building tools to help people design, help engineers design better software systems, and that's making me really excited. Because I got to sit down with the guy whose company verified the software for the Boeing 787, and he told me about the software system that they built, which allows them to track the register values after every step of execution of the software, all the way back to the high-level requirements for the plane. I said, that's amazing. I want something which provides me with 1/10 of that for my software systems, but that's a 5-year engineering effort. And even if I can have that for the software that Akamai builds, I need that for OpenSSL, I need that for the Linux kernel. And that's just a level of software engineering effort that I don't have to put in. So I think that there's a lot of opportunity. I think some of the stuff we're doing around like Nixos and containerization and virtual machine configuration management starts to get us there, but there's so much further we could go. Some of the stuff around like software verification is really exciting too, but it's obviously like not baked yet. So it's a truism within the industry that software sucks, but the tools and techniques that Nancy is talking about are the first thing which has convinced me that it might be possible for us to build software which we can convince ourselves is safe, systems which we can convince ourselves is safe out of this sucky software, assuming that we can figure out how to apply these tools and techniques to the problems that we have. So my call to action, to be really explicit about, is please go read Engineering a Safer World. It's an excellent book. If you read only the first chapter, you will begin to understand why it matters. And there are some of the accident analyses around chapter 4 which get really interesting. You can, that's the horror stories. And some of the analysis later in the book starts to lay out the ways that Nancy thinks about breaking these problems down. So also, Nancy believes so much in this book that she negotiated with the publisher to take lower royalties in exchange for them putting a free PDF online. So the cost of the book should not be a barrier here. There is a free PDF on the MIT Press website. Go download it right now. So also, join us at the PSAS conferences over at MIT. There's a nascent sort of security group there. They're mostly from the military. Akamai are really the only other application software company there, and I would really love to see all of you there, because I think that we're working at a scale where we need these tools. I think that there's a lot that we can learn from the people who are at these conferences, and I think that there's a lot that we can bring to them from our experiences of working at really complex systems. And so help us build tools to make this stuff go. Because it's an engineering effort which is going to take the whole industry. It's not an engineering effort that any one company can do. So help us apply these techniques. Help us boil this 500-page book down into something that engineers can use in their day-to-day lives. Help us understand the constraints our systems need to uphold in order for them to be safe. In short, help us engineer a safer world. Please and thank you.